Hello, welcome to the American Ceramic Society's course on firing of ceramics. My name is Dennis Brosnan, and I have partnered with the American Ceramic Society in order to provide this course on Zoom. I'd like to say that I've been a member of the American Ceramic Society for a lot of years. I've seen it change and evolve, and I'm very pleased that they are continuing with their lifelong desire to be an educational resource in the field of ceramic processing. In my career, after going to university and graduate school, I actually went to work in the field of ceramics in research positions to start with, and later into management. That actually was part of my education after the university, and learning how industrial processing took place and how the advent of a new product came about through research and into plant production, into plant trials, and finally into normal production. I served in that capacity, making refractories first, refractory ceramics, both shaped refractories as bricks, and what are called monolithic refractories, plastics, castables, ramming mixes, gutting mixes, things of this particular nature. Later on in my career, I worked for people that made technical ceramics, including insulators, electrical insulators, and things of this nature. So I've had quite a bit of experience in processing ceramics, both from a very controlled environment of controlled composition, controlled mineralogy, very specific property goals, into the latter part of my career, which was the university part of my career, where I was hired to manage a research center for the clay brick and ceramic tile industry in the United States. So the clay brick portion of my job became known as the National Brick Research Center, a component of Clemson University. It's the longest term College of Engineering center at Clemson University. I partnered with the Tile Council of North America to provide research space for their personnel, and we performed research on both clay bricks and ceramic tiles. It was very interesting to work with clay bricks because that's the least controlled of all substances that are processed into ceramics using natural materials and based on the variations of the natural materials. So clay bricks were vitrified ceramics, meaning when they were fired, glass was formed. And when the ceramic was cooled in the kilns, the ceramic became rigid. But in the other ceramics, other types of mineral reactions took place in firing. Vitrification may have played a part, but not the major part in forming the bond and achieving the final properties of those ceramics. Now, when I was a university professor, I taught in the classroom you can see behind me. And I taught this subject for a lot of years. So I'm looking forward to getting started with this class with you on the Zoom platform. There will be a number of classes divided into 3 units. Of course, this is class number 1, an introduction. And this is unit 1, which is part of the introduction. And we're looking at the firing changes within the ceramic. We'll go to other units where we look at kills, and finally at the environment. Now, most university professors that are in the field of science or engineering have never taken many engineering courses, but I did have never taken many education courses. but I did decide that I wanted to take an education course, and this course was about formulating learning objectives. So here's what I hope that you will achieve during your time taking this course. And the first bullet item is to use physical properties, physical and chemical data obtained through a laboratory test, analytical test, and physical property test to optimize the firing process. This is the proper way to do this, and that's where we're going to start in Unit 1. We want you to understand the chemical reactions and physical processes that happen during firing. These are internal to the ceramic. And once you understand these, then you can understand how to optimize your firing process in order to obtain the best possible product. In Unit 1, the first unit, we want you to recognize the source of firing defects that certainly happen in producing the ceramic. We'll go on to unit number 2, where we will supply the temperature and the energy that's needed to form the final properties in the ceramic, the permanent properties of the ceramic, make them strong and functional according to what needs you have. And that means we have to understand kilns and furnaces, understand where the heat goes in firing, not only into the ceramic, but into the furnace heat losses, and to heat that's vented to the atmosphere. So the key question is how much heat and how to use that heat in the most efficient manner. So that's Unit 2 of this course. And finally, we're going to look at environmental emissions. I'm not trying to make an environmental engineer out of you, but I want you to understand what the sources of emissions are. I want you to be able to speak to people within your company or within your organization. I want you to be able to speak to the public if that's your role in the organization. So that's the third unit and the shortest unit in the course. So we have some fundamental questions in this course. The first of these is, how much temperature do you need? Actually, ceramists, ceramic engineers will call this, how much heat work do you need? Because you use heat to perform work. Thermal energy performs work in densifying the ceramic and giving it its properties. So how much do you need? And how do you figure this out? And that's, of course, Unit 1, starting with today's class, the fundamental question, how much temperature? The second question of this course is, how do you supply that temperature, or as we now are calling it, heat work, in an insulated enclosure that we call a kiln or furnace? How do we get there? How do we manage that amount of energy that we're expending? So that's Unit 2, and as I said, then Unit 3, what are the environmental consequences of firing? So we're going to take this journey and answer those 3 questions. And of course, we're starting with Unit 1, how much temperature? In order to figure out how much temperature, there's several ways to do this. And we're going to look at those particular ways in today's class. That's the most important thing in today's class is, how do you figure out how much temperature? So we're going to look at chemical and physical changes in the firing of ceramics. The foremost physical change is densification. The ceramic shrinks during firing. But not always. There can be expansion reactions as a consequence of the minerals reacting that counterbalance some of the shrinkage. So we need to be smart and knowledgeable about what these changes are in processing of the ceramic. So that's where we are today, just getting started in Unit 1 of 3. So here we are, Part 1, the introduction. This is one of my favorite mosaic tile structures that humanity has produced. The reason is that you see behind you a chamber kiln. You can see a smokestack and individual chambers. And so these chambers If you can see, my pointer are open, okay, and individual chambers are where the product went into the kiln. Below this is a trench, and in this trench is where the burners were. This would be a solid fuel fired kiln, so you can see wood that's piled up over here in the upper left to be used by people who are feeding the burners. The product itself, a ramp was put across here. The product was loaded into a cold chamber, and then that chamber was successfully heated by hot air that was channeled over into various of these chambers. The air was moved by the chimney effect, the suction created by the chimney, because these early kilns obviously had no electricity. And so here are people that are forming bricks in the foreground. So apparently this is a brick kiln. Interestingly enough, it's covered by a ceramic tile to keep any rain off the kiln while it's being fired. So we're going to talk about some of the older kilns that are used in technology before we go to the modern kilns. So let's talk about firing. You see my definition as the first bullet point. The process of heating formed ceramic shapes to high temperatures, typically those exceeding about 1,000 degrees Celsius or exceeding about 1,800 or so degrees Fahrenheit. That means that the interior of the furnace is beginning to glow red. The emission of visual light from the inside of the furnace is red in color. And that amount of temperature is required to activate processes that make the ceramic densify and become permanent in their physical properties. So that's what we're trying to do. We're trying to reach a physical property goal, and typically strength is one of those, but they're and permanence of shape is one of those. So that's the sentence that I used in my description of this course. But I'm very fond of referring to Professor Dodd in his Dictionary of Ceramics, which is an old book that's been reissued. Mine is 1967. That's pretty old. And Dodd says firing is the process of heating ceramic ware or objects in a kiln to develop a vitreous or crystalline bond. Vitreous meaning glassy bond, or crystalline bond meaning one that's a component of crystalline substances that have regular structures, not like a glass, which is amorphous, thus giving the ware properties associated with ceramic materials. So you always have a goal in firing. And so one of the things we're going to answer is, what are these chemical and physical properties and how are they attained? Particularly the next lecture, we're going to review some of the physical properties that are very much pertinent to this particular course. I'm not trying to turn you into a lab person, although you might be a lab person, but some of the properties that we will look at are very important in describing what the consequence of firing is, what the heat work accomplished. So here's principle number one in this course. We're going to start with raw materials. The raw materials to the left are a kaolin in the top left. These are blocky particles. It probably was a fairly plastic kaolin, not the type of kaolin that you might use in a casting process, which might be a coarser kaolin with more separated kaolin platelets. And the lower picture is a shale. Shale, in this case, has flake-like particles. And somehow these particles, we're going to mix them together in a ratio that we want. Typically, ceramics are processed by more than one natural or synthetic mineral that are added together with other things like binders and plasticizers and lubricants and water. We're going to form them by some process. I know that many of you will have taken some of the earlier courses in this sequence, and so you know a lot about forming. The goal in forming is generally to get the maximum density that you can, although sometimes you don't want to achieve very high density, particularly in thermally insulating products. We're going to process them by forming them. Then we're going to dry the water out. And perhaps you've taken the course on drying that I was the professor in. And finally, we're going to take them to a kiln. This is a tunnel kiln. These gentlemen are standing beside a very long tunnel kiln. And so you can see the ducts on top of the kiln where air movement is taking place. This is the cooling zone of the kiln because air is being blown down to remove heat from the product as the product goes, in this case, from your right to the left in the processing step. So you've been taught to achieve the best possible properties in processing prior to firing. And in firing, we're going to generally get densification, permanent bonding between the particles. That's what we want to achieve, but we can't do it all in the kiln. The kiln will do its job. The firing process will do its job, but you must have the best possible product entering the kiln in order to let the kiln do its job to the best extent. So here are some thoughts on kilns. I want to just basically mention some of them. Kilns are thermally insulated enclosures to concentrate heat from some heating source, usually the combustion of fuel, and usually the combustion of natural gas, but other fuels are used, including solid fuels from time to time. Maybe coal is still used in many parts of the world, or wood is still used. And of course, electricity can be used in resistance heating devices in order to achieve the heating process. There are many types of kilns, intermittent kilns, or you might call them box kilns or periodic kilns. There are continuous kilns like roller hearth kilns. The kilns are used for things other than making shaped products. They're used for calcination or heating of ores or minerals. They may be shaft kilns or multiple hearth kilns or rotary kilns. So there are all kinds of kilns out there that you might be involved with. And this course is going to be generally applicable to all types of kilns. So there's a little bit of history here, which I borrowed from Wikipedia, which would tell us that many of the origins of fired ceramics go back to the Middle East, and some of these origins go back perhaps as much as 25,000 years ago or more. That's an incredibly long period of time. According to Wikipedia, other areas of the world learned how to use heat to create permanence in ceramic materials. And of course, we know that Japan and parts of Africa, parts of Asia developed a lot of firing technology. And of course, that was true in South America and in the New World as well, the Middle East. So who invented firing of ceramics? I don't believe we have any idea. We don't know, and it's not important. Fired bricks, because I have spent a lot of time working with bricks, originated about 3,500 years ago in the Middle East. And there's an excellent book, if you have any interest in bricks at all, by Professor Jim Campbell, called Brick, A World History. I happened to be able to see Dr. Campbell give a presentation on ceramics from the Middle East a few years back. It's an excellent book, so I recommend it highly. So we'll look at some kills. These are some early kills from American history. I'm going to talk about these kills just a little bit, and I'm going to change my pointer over. Hopefully that won't take but just a second, so please bear with me. There we go. And now we have my my cursor illustrated as a laser pointer. So these are a couple of early American kills that I'm aware of. This one right here is showing a person after the American Civil War. So fortunately, we can think of this as a free person laboring, and he's adding long pieces of wood into openings called burners in the base of the kiln. The bricks that are stacked up in this kiln are in the upper portion, so the heat from the combustion is naturally rising by buoyancy. Those of you that took drying, the drying course, remember that I talked about hot air being a lower density than that of cold air, so hot air always rises, and you can see the black smoke, the environmental emissions out of this early kiln. Because the air is moving from the burners upward using buoyancy, it's called an updraft kiln. The draft or movement of air within the kiln is moving upward. Okay, so these were used typically to make bricks and pottery. And this particular picture is from the museum in the city of Charleston, South Carolina. So I took a picture of a picture. The other picture is a picture of a stove kiln, which also was an updraft kiln. If you look closely, you can see openings for burners right at the base of the kiln. And it had a permanent brick structure along the forming outer walls. So the bricks were laid on the inside and stacked up, and then the furnace was fired. Of course, the firing cycles here were typically around a week or perhaps 10 days or so. It took a long time for the ware or the bricks inside the kilns to cool off so that they could be handled to be taken out. Interesting story about the stove kiln on the right, which sometimes could be called a field kiln, is that I'm driving along a highway with my family in the state of Montana near a town called Deer Trace. And I looked out the window and I said, "Look, there's a kiln." And my family moaned, okay, because they knew what was going to happen next. I had to get out and go tromp around in the field here and look at it. And actually, there was a manufacturing building where bricks were made and tunnel dryers there. The time frame is early 1900s here. And there were two stove kilns here. Two kilns meant one could be being fired while the other was being loaded and unloaded. Then adjacent to that were 4 downdraft kilns. The stove kiln is an updraft kiln. And so my family had to wait patiently while I tromped around and took pictures. They have forgiven me for this, but it was near a territorial prison in the state of Montana. Well, it wasn't a state at that time, but nevertheless, that's how I found it. I just happened into it. Early American kilns morphed or evolved into downdraft kilns. So here's a small downdraft kiln. It's been restored. The burners were here. You can see the fire bricks forming an opening. And so solid fuel was used to burn inside these burners. And the hot gases went up toward the center, and they were sucked down through the middle using a chimney effect. So the heat went up, but then it was drawn downward, and there's a replica of a chimney, not an actual chimney here, to show how this might have worked. Of course, to restrain the the kill from the thermal expansion, there were these metal straps or bands around the outside of the kill, trying to hold the bricks, the fire bricks on the outside in compression so that they would not tend to spall. Of course, there's a dome or a crown on top of this kiln that's round. So the air moved upward and came down in a downdraft kiln, still solid fuel fired before the time of electricity when we had fans to move air around. Another downdraft kiln is a chamber kiln of this type. Obviously, it's not in good repair, but this one could have burned solid fuel and then converted to natural gas. The air was drawn downward and upward into individual chimneys. So the draft in a kiln or air movement was important in history. Now, contemporary kilns take on many forms. This is a kiln in my laboratory in the National Brick Research Center, and these were some of my students in a course that I taught. It has a car. It's an intermittent kiln, meaning that you place the car with whatever ware you're firing, you roll it into the kiln, shut the door here, and start the process. So we always fired objects as a part of the illustration of how to get final properties. The kiln on the right is also an intermittent kiln. It's also a gas-fired kiln, and it also has a car. So the car is loaded and it's inserted into the kiln and it's heated up. So there are a couple of things that I notice about these kilns, and perhaps you do too. I hope you do. The insulating material or refractory material is different in these two kilns. The one on the right has fire bricks. You can see the brick patterns here on the inside of the kiln and the door of the kiln, which swings shut, and the car. Yet in my laboratory kiln, you can see that it's fiber ceramic insulated. Okay, also the kiln car is fiber ceramic, and these posts hold saggers or plates which hold the ware suspended into the kiln atmosphere. I can tell from looking at this that this kiln has a temperature limit of around 3,000 degrees Fahrenheit. Okay, just from the fact that most of the fiber will shrink appreciably when you get above 2,900 degrees Fahrenheit or thereabouts, and get into the realm of 1,400 to 1,500 degrees Celsius. This kiln on the right is lined with Super Duty refractory brick, which have a temperature limit by definition by the American Society for Testing and Materials, the regulatory authority for ceramics and refractories in the United States, 3,000 degrees Fahrenheit. So there's similar temperature limits on these kilns, but they are lined with different kinds of insulation. Lining means the enclosure that contains the heat. So these are intermittent or box kilns. A lot of laboratory kilns are box kilns that are electrically heated. Now here are a couple of continuous kilns. This is the roller hearth kiln in my laboratory. So individual ceramic rollers propel ceramic tiles, in this case, along the length of this kiln. They're one high, they're not stacked up, and they are heated up gradually. They get into the hot zone of the kiln where the highest temperatures are, and then they're cooled off. And so we can see the kiln stack in this end of the kiln. This is a tunnel kiln. I must have taken this picture in Europe. So there are railroad cars that I call them railroad cars or kiln cars that are on flanged wheels that go down tracks in this kiln. And so the door's going to open, and the cars bearing the product are going to ride down the kiln, gradually being heated till they get into the hot zone or burning zone of the kiln, and then the product cools off. So there are all kinds of kilns of different scales and different magnitudes. So remember, we're going to focus on kills in Unit 2 of this course. Well, we're in Unit 1, and so we can talk for a bit about viewpoints in the ceramic. And this is going to take us in this part number 2 into centering. So here is my friend John Dowdle. He's now retired, but he's pictured at the exit end of one of the kilns making paving bricks, clay bricks as pavers that are exiting the kiln. And he's looking at these pavers, and with his eyes, he's looking to see if they deformed. He's looking to see if there are any cracks. He wants to look at the color. So he's very interested in this. So this is the almost the end of the processing step. Of course, once they exit the kiln, they're going to go into any quality control and inspection and packaging steps. Of course, you can look inside the ceramic. One of my fields is microscopy, so the upper picture is a fairly low magnification picture of a red brick, just like John Dowdle is making right here. And at very low magnification, we can see grains of quartz that survived the firing process as quartz. It didn't transform into another mineral. It's all fractured up. And we'll talk about why that happens in volume transitions that take place in heating of quartz and additional volume transitions as the quartz is converted to other minerals. But these quartz grains, there are a few of them here in this picture, are surrounded by what we would typically call a matrix. The matrix is the vitrified ceramic that was formed by the firing process, and the black spots are pores in the ceramic. They're black because we're only seeing light that's reflected directly upward, and the pores tend to scatter light, so they appear to be black in this photograph. If you go to a little bit higher magnification, then in fact, we can see the black pores again, but we can see a gray continuous phase, which is the glass that was formed in partial melting of the brick in firing. Not total melting, but partial melting, just a small percentage of glass. And within that glass, there are white streaks, and the white streaks are hematite, okay, that are reflecting the light visually from the macroscopic view, which John Dowdle is looking at. He's looking at a red brick. But when looking on a microscope, we're going to see a white color where the hematite is located, the red iron oxide. So you see, we've got two viewpoints. That's why this course is developed into a Unit 2, a view outside of the ceramic, and a Unit 1, a view inside of the ceramic. Now, those of you that took drying know that I took exactly the same approach to the drying course, the view inside the ceramic, what's happening during drying, and the view outside the ceramic, what's happening in the dryer. Well, we're going to do it again. So let's go forward in this part number 2. What we want to do is develop what's called a fired bond through the process of sintering in firing the ceramic. So you've heard about sintering before in earlier courses, but I want to expand on the idea of sintering to make sure that you understand there are at least 3 types of sintering that we will talk about in the course. With clay ceramics, we talk about vitrification. Vitrification forms glass within the ceramic at elevated temperature, as I just mentioned in the case of bricks. The glass solidifies, becomes rigid, and provides the major source of bonding within the ceramic once it's been processed. Clay ceramics are called vitrified ceramics, and there are many types of vitrified ceramics, ranging from crude clay ceramics to porcelain products. They're very different in their mineral constitution, in the fired state, but vitrification took a large part in producing the mineral structures that are present in the ceramic. Now, in many technical ceramics and refractories, we have a process we call reactive sintering. That means that we heat up the ceramic. We typically form some amount of liquid phase or vitrification, if you want to call it that. And as we continue doing heat work and continue firing the ceramic, the liquid phase begins to disappear and new minerals are formed. I call that reactive sintering. So once the ceramic is cooled off, a major part of the bond between the particles are new mineral structures that are formed in the firing process. There may be some glass left as solidified material, but that's reactive sintering. Now, in advanced ceramics or high purity ceramics, solid state sintering takes place. That means that there's very little or no liquid, no transient liquid that's present, and atom movement is by diffusion to points of contact between particles that form the solidified bond, the fired bond in sintering. So the objective of sintering is to achieve that fired bond at particle-to-particle contacts to reduce the porosity that's present in the formed ceramic and to give it its strength. There's another term used here, pore size distribution. Porosity is the total amount of void space in the ceramic expressed as a percentage of the total volume of the ceramic. So we're going to say that we have a certain percentage of porosity. And as we go from vitrified ceramics, we'll have high porosity, typically maybe above 10%, as much as 15% apparent porosity. That word apparent means open porosity, porosity that we can measure. As we go into technical ceramics and refractories, typically we will have less porosity. Perhaps we will have maybe as little as 3%, 5%, 8% apparent porosity achieved in reactive sintering. In advanced ceramics, we typically would like to be as small in porosity as we can be, below 1%, maybe perhaps below 0.5%, 0.5%, to achieve the maximum possible strength at room temperature and at elevated temperature. But basically, there are three types of fired bonds that can be formed depending on the chemistry of your system. The chemical analysis for clay ceramics tends to favor vitrification because of the lower melting points of the liquids. These melting points are typically just below red heat, and we can start forming melted phases within the ceramic then. In technical ceramics and refractory, the chemistry may be much more pure. I know there are clay refractories, but in the general case, there are much purer ceramics. We've controlled the purity and manufacturing. And so typically we'll use higher temperatures in producing these types of ceramics above red heat. And in advanced ceramics, we can really achieve sintering maybe as hot as white heat in a kiln when the visible emission from inside the kiln lining is white in color. You know that you're very close to 1700 degrees centigrade Celsius, maybe 3200 degrees Fahrenheit. Whereas remember, red heat was down here close to 1000 degrees Celsius when you can see it. Now, this is an illustration you'll see again comparing vitrification sintering to reactive sintering. So we're going to pretend that the circles here represent particles. Okay, now I know that particles in ceramics are rarely good spherical in shape. I have made some ceramics myself out of glass spheres, microspheres, and they were, and spherical shapes perform a lot different in processing than do angular particles, which tend to pack. But nevertheless, we're going to assume that we have spheres. Now, spheres have points of contact, okay, and we're illustrating 3 spheres here with 3 points of contact. And what I want to say is, at the point of contact, right immediately at that point is the highest possible surface energy in the ceramic. So the ceramic will act predictably when melting starts. Typically on the exposed surface of the particles, the liquid will migrate to these points of contact, and it will tend to smooth out that point of contact to the point that we get a little radius here along the liquid that's formed there. If we stop firing at that point, we can see that on some type of microscope. But nevertheless, vitrification is about forming a liquid phase which tends to migrate toward points of contact in order to reduce the surface energy of the ceramic. Reactive sintering is different. We have the same 3 spheres in our little theoretical model of sintering here. We form some liquid in the early stages of heating, melted phase in the early stage of heating. But then during the process of sintering, diffusion takes place from inside the ceramic particles toward the surface. Diffusion, atom movement. Atoms move toward the surface and changes the chemistry of that liquid such that new minerals are precipitated or formed by direct reaction at those points of contact. So the new minerals can become part of the bond phase. Okay, so in that situation, the liquid phase may be disappearing. It could be transient in nature. Transient means it's only temporarily there, and the new minerals can form the permanent bond in the ceramic. So that's the difference. In the case of vitrification, we form a liquid, and in fact, we can form some minerals, particularly in clay ceramics, a mineral called mullite we'll talk about later in the course. But in reactive sintering, the liquid primarily disappears or becomes not the major factor in the bonding between these adjacent particles. So those are 2 types of sintering processes. And then here's the 3rd type, which is sintering with no liquid phase present. And in this particular case, we still have the illustration of 3 spheres being in contact, or 3 circles being in contact here. But in this particular instance, while we have the high surface energy at points of contact, surface diffusion, movement of non-liquid phases, but atoms are going to move, particularly cations, along the surface. You can say they're going to jump along the surface or diffuse along the surface, and diffuse from inside the particles, inside the bulk, into this point of contact, and they're going to deposit new crystalline material at these points of contact. The reason that happens, again, is minimization of surface energy in the particles. So the driving force for sintering is that minimization of surface energy in order to consolidate the ceramic. We're going to talk about these processes in detail as we go along. I can tell you, as an undergraduate, as a senior level student, I took a course called Solid State Ceramics. And I thought that this is how all ceramics were made. Okay, that solid state sintering was the way that you made everything. Then I went into industry, just going back a slide, and I made refractories. And all the refractories I made were made by reactive sintering. Later on, I made technical ceramics, and they were made by reactive sintering. So a liquid phase plays a role in the largest volume of ceramics that are produced in the world, in the globe, whether it's vitrification or it's reactive sintering. That's the largest volume of material. And as a senior, I thought wrongly that everything was made by solid state sintering, certainly anything that would be extremely interesting. And then I went and worked in the traditional ceramic field and found out that my viewpoint was incorrect. Okay, well, the key question of Unit 1 of this course is how much temperature is needed. So what do you do? Do you get a box kiln? This is an electric heated kiln called a heavy duty kiln, one that I'm very familiar with. And here's a gentleman that I know very well who is portrayed as putting a brick into a kiln. Well, this is just a publicity stunt. His name was Gilbert Robinson, that formed the ceramic engineering department at my institution. But I'm using this picture because I like it, but also because how much temperature? Is it trial and error? Do you take ceramics and heat them up to a sequence of temperatures and measure their properties and decide what the firing temperature should be? Perhaps that's been done throughout history, temperature and time. And some of those early updraft and downdraft kilns, there were people who could gauge the temperature by the color of light emitted from the kiln, and they knew how much time they'd been firing the kiln. They looked at subsidence of the load in the kiln. They had ways to do that, and they knew when the ceramic was mature. The word mature means the ceramic has developed the properties that are needed for it to be functional. So how much temperature? You can do it by trial and error, like this gentleman is kind of illustrating here. There are other ways to do it. And another way to do it is to use a map called a phase equilibrium diagram. We had maps in drawing called psychrometric charts. This is the map that we use in firing, and this is a two-component phase equilibrium diagram. So in this particular diagram, we have a diagram of the lime silica phase equilibrium diagram. So the point right here on the diagram is 100% silica. The point right here on the diagram is 100% calcium oxide or lime. So there's things that we're going to talk about. You're going to become very familiar with this diagram, but you can see we got compositions like this is 80% silica and 20% lime, I believe. And we can see that any given temperature on the temperature scale here, at equilibrium, we should form certain minerals or phases as they're called, okay? And so depending on the composition, we will form what you see here. Everything up in the upper portion of the phase diagram is melted phase. So nevertheless, we cannot certainly make a silica refractory brick. That's the example here. For silica, we can't make it and melt it because it would have no shape and no functionality. So we've got to have it come through the firing process, come out of the kiln, looking like a brick of the dimensions that we want to have. So I want you to notice there are certain points that are V-shaped here. These are called eutectic points. Eutectic is a word that means lowest melting, E-U-T-E-C-T-S-C, eutectic points, lowest melting. So here's one. There's another eutectic point here, another eutectic point here. So in order to make a silica brick, which is made out of silica aggregate called ganister, a natural rock, if you just take it and fire it in a kiln to develop a permanent bond, you're gonna have to get to some pretty high temperatures until you start forming liquid. But you can add to the amount of liquid that's being formed by adding the flux or the lime to it. So by adding a small amount of lime, let's say 1 or 2% maximum, you'll form more liquid and you will form it earlier at the eutectic point. So for years, lime has been used as a flux to create bonding in sintering of silica refractories. Sometimes people call this a flux bond. So here's a little story from the Journal of the American Ceramic Society, one of the earliest issues about 1895. One time I had to go back in the literature in order to research the origins of certain things that were happening in refractories. And I found this story, and I just love this story. So the story was about a company in the late 1800s in the Pittsburgh, Pennsylvania area of the United States making silica refractories for use in iron furnaces. And so the company wasn't making the best silica refractory brick that were possible. Another competitor was making much better ones, and those folks didn't know how to, the ones who were making the poorer brick, the one that wasn't so good, said, we're going to find a ceramic engineer. Well, in 1895, you pretty much had to go to Europe to get a ceramic engineer. There were no schools of ceramic engineering in the United States. So they hired a British engineer, and he came over and he improved their product instantly. And so he would walk out to the mixer when they made a mix, and they might have made one in the morning and one in the afternoon. Remember, the mixers were not electrically powered back then. They used animal power in the mixers. So he took a large container of liquid that was black in color and poured it into the mix. And the mix churned around like a Muller mixer, like a mixer that was throwing the material around until the particles of Ganister were wet out. They fired the product, and it was wonderful. It was as good or better than the competitors. And so they really appreciated having this guy bring over this trade secret of how to make a good silica refractory. But, you know, they were a family-owned company, and perhaps they weren't the most honest. And so they wanted to figure out what this British engineer was doing. So they spied upon him. They hid in his office and watched him mix a white powder with water and with ink used in pens and penmanship in writing. The ink was there to color the liquid and to disguise what was in the container. Otherwise, it'd be white in color from the solid powder that he'd added. So he mixed it up, went out to the mixer, poured it in. Well, of course, at night, the family members snuck into the office and found out the white powder was lime. It was a flux. So it's this system right here. You add the right amount of lime to silica, we're going to form liquid, and we're going to make a quality ceramic. Well, unfortunately, the family was not honest, and they discharged the British engineer. I guess he went back to Britain, and perhaps that says a lot about ceramic history or about American industry during that time period. But so what I'm trying to get to here and telling this little story, or parable, if you want to call it that, was that the British engineer knew that the flux, the lime, would create liquid within the ceramic. So we can use phase diagrams. We can use maps like this to figure out where the eutectic points are in our systems. Sometimes, of course, the systems have multiple components, not just two components, like silica and lime. but we can use phase equilibrium diagrams. So that's a much more refined approach than just guessing, than doing draw trials, okay? Trial and error. So the phase equilibrium diagrams are going to help us understand what kind of temperature we need in firing the ceramic in order to make it have permanent properties. There's an even better way to do it. I'm sure you're not surprised, and perhaps you're aware of thermal dilatometry. So here's a device for measuring thermal expansion in my lab. This is our research grade dilatometer made by a German company, Netsch. And here's the furnace right here. Okay, in the lower picture, you can see the furnace. There is a ceramic tube that holds the specimen. There's a push rod inside the tube where the length of the little specimen inside here, which is typically, in our case, about 20 millimeters in length by about 4 millimeters in width and breadth. So nevertheless, a small specimen is used. The furnace is slid around this tube and it's heated, and you're continuously monitoring the length. So the graph here is showing the length of the ceramic. Notice the negative numbers, meaning we're expecting it to shrink versus temperature. So the purple line or upper line in this graph shows the ceramic expanding as we begin to heat it. In other words, it's upward direction, but it gets to a point of inflection here. The point of inflection is where shrinkage begins. And so if we know that point of inflection, sometimes called incipient fusion, if it's a vitrified ceramic, incipient means the beginning of fusion, then we'll start seeing dilation or deflection, shrinkage. Okay, and shrinkage in this particular example begins to take place at a particular temperature indicated up here below 1,000 degrees, between 800 and 1,000. And then we get more rapid shrinkage taking place at an upper temperature just above 1,000 degrees Celsius. And we'll continue shrinking as we continue heating until we get the amount of shrinkage that you want. On this graph, we show around 6% or so shrinkage. That's really too much shrinkage in a practical sense, because it's hard to make a ceramic with more than about 1.5% linear shrinkage without its cracking. In the drying course, I talked about the volumetric shrinkage being about approximately or about 3 times the linear shrinkage. And so if you're above about 1.5% linear shrinkage, then you're going to be above about 4.5% volume shrinkage, and that's a lot of shrinkage in the ceramic. You'll learn in this course that there's some inflection points here. The derivative of length versus temperature is shown here. Delta L over L, or derivative of length over unit length, change in length per unit length versus temperature. When it goes up, it shows an inflection point. So that's going to be here right around 500 degrees Celsius or so. And you'll become very familiar with identifying that that's probably due to the quartz inversion, which goes from alpha to beta quartz at that particular point in time. Don't worry about the definition of alpha and beta quartz. It's just an internal change in the ceramic for today's purposes. You'll also learn later in this course that the incipient vitrification, the first amount of shrinkage, takes place when the lowest melting glass melts in the ceramic. So that's probably going to be a very high alkali glass in a vitrified clay ceramic. And then we begin to get higher temperatures, and a second glass, which contains a greater amount of alumina because alumina was dissolving in the glass during this period, it will vitrify here. So the shape of the curve and the derivative curve, which tells us when things are changing, meaning incipient fusion where the derivative goes negative, and the second point of fusion when the derivative goes even more negative, tells us about the shrinkage. So we can use these points of shrinkage, points of inflection, to tell us the temperatures at which we expect to fire the ceramic. So typically, if someone would come into my laboratory and want to say, well, here's a new clay that we're mining, and we want to mix it with another clay, maybe one clay for its refractory properties, lack of shrinkage, and one because it's highly plastic. Tell me what the mixture should be and what the firing temperature should be. And typically, we would resort to thermal dilatometry to get a first look at that question, and then later on make larger scale specimens, not something that's 20 millimeters long, but maybe quite a bit longer, bigger specimens, real size bricks. Okay, so we went through the key question. What is the temperature of firing to give us the properties we need in the ceramic? And we decided we could do that by trial and error, and that was one way used throughout history. We decided that we could do it with phase equilibrium diagrams, and phase equilibrium diagrams generally became known in the early 1900s. They were determined then, and engineers and scientists started using them, particularly as we approached the 1940s. We also decided we could use thermal dilatometry. Now, you can go back to the idea of heating to various temperatures and measuring to shrinkage after a sequence of temperatures, and that works pretty good, but dilatometry is a much faster way of doing that. So we answered the question. We had an idea on how much temperature was needed, but we didn't have an idea on what the required properties are. And so I want to go over that, depending on how long you might have been associated with the ceramic industry. You may know all of this or not know some of it, but the first group that defines properties are consensus or national standards. And in America, it's the American Society for Testing and Materials, the Canadian Standards Association. We have international standards here. In Europe, you have European Normal standards, European standards. So consensus standards are used on a lot of products, but not all. Particularly consensus standards are formed by national committees of users and producers and interested parties that get together and vote on what the values of the standards should be. So they will publish a standard and says for a product to be classified as a particular functional product like a ceramic tile, a ceramic whiteware product, a brick product, a refractory product, it has to exhibit certain properties, and these are published by consensus. Now, of course, we understand that there are some standards that are not published this way. Some are consumer standards, meaning a company that buys a ceramic product may establish its own standards, or there may be consensus standards and consumer standards as well. For a lot of refractory products, when I was involved in that industry, most of the consumers had their own standards that they bought products by, which were keyed into testing methods and properties expressed in the consensus standards. There are military standards if you're supplying a product to the military or government. There are certainly proprietary standards. In other words, standards that are kept secret, that are not published. You may have your organization's own internal standards, and these may be secret. And they're usually keyed into some consumer standard so that you know how to make your product that will be the quality that your organization requires. And then, of course, there are regulatory standards that are keyed into some things like energy consumption requirements and some of the products that you have. So there are all kinds of ways that people define what a good product is. What what a good ceramic product is one that meets standards. I am from time to time asked by people from other parts of the world than the United States, is this a good brick or a good tile or a good refractory? And my answer is always that if it meets the national standards in your country, then it's a good product. I don't make any statements on the degrees of whether something is better than a good product. It's just a good product if it meets national standards. So here are a couple of standards. These are ISO standards for ceramic tiles. I just circled a strength performance standard. This is very common in ceramics to have a strength-related physical property standards, perhaps expressed as a breaking strength or a modulus of rupture, a strength in bending of the ceramic expressed as a modulus or characteristic of a particular product in a defined test. So that's one for extruded ceramic tiles. Here's another one that is for porcelain products, toilets. And I just took the ASME standard for vitreous china plumbing fixtures in the United States. And so I highlighted a couple of things that here there's an absorption standard of 3 test pieces that shall not exceed 1%, excuse me, 1/2 of 1%, 0.5% absorption. Well, a vitreous china object is one that you don't want to transmit water. In fact, these articles are typically glazed to make them impermeable to water and to provide colors. And in this particular standard, there's also a breakage standard that the object has to support a 300-pound weight. Now, I have in the United States been involved in some cases where toilets have broken when being used. This is not the subject of this course, but there is a standard that they must be able to support a certain load. And that's where you start in any legal situation involving these products. Okay, well, I want to talk to you about some dimensions and literature resources. In the drying course, I usually used inch-pound dimensions, British standards, inch-pound standards, which included things like the British thermal unit, which ironically the British don't use much anymore, if at all. We still use these dimensions in the United States. So particularly when we get into the combustion section in Unit 2, you'll hear me talk about British thermal units. But it's okay if you think in other dimensions like kilocalories, you'll be able to adjust the applications for using SI units, metric units. Also wanted to mention some literature resources. You don't need any of these for this course. So they're not included with this course. There's no book accompanying this course, but I will mention some of them because you might have them in your corporate library or in an engineering library in a university that you might have available to you. So the first one that I'll mention is Grimshaw's book on the chemistry and physics of clays. If you're making a vitrified ceramic, this is a book it's very old now. It goes back to the World War II years, but Grimshaw wrote a great book about firing vitrified ceramics. It has phase diagrams and it talks about refractories. It's a very difficult book to use because if you look in the index under any particular topic, you'll probably find numerous citations, numerous pages where that subject is discussed. And so you're going to have to look at quite a few pages to garner all the information. But it's a good book that I like. I have. It was reissued by a company called Tech Books in about 1960 or thereabouts. I taught from this book early on when I became a university professor, only for a few years, and then used it as a resource. Fortunately, when I became a university professor, I was asked to become a registered professional engineer, which means in the United States you have to take a test and prove your knowledge, even though you have a university degree, which I had 3, but I had to take this test. And that's an open book test. You can take as many books into the test as you want. The test lasts up to 3 days in length. And so I took this book, Grimshaw's book, into the test. Well, just so happened the guy that wrote the test took all the questions out of Grimshaw's book. So I was teaching out of this book. I knew where everything was in this book. I could just thumb through it and find the topics because I was very familiar with the organization of the book. And I answered all the questions correctly, or most of them anyway, and became a registered professional engineer. So you might find the chemistry and physics of clays in your corporate or engineering library. Another, of course, fantastic book is Introduction to Ceramics by Bill Kingery. The later edition showing here, published by Wiley, is a great book. It's a very thick book. It's the book that I used as a senior in ceramic engineering. And so most people are going to be familiar with Kingery. Bill Kingery was a professor at the Massachusetts Institute of Technology, MIT, as it's known. I happened to have the privilege of seeing him give a lecture. So he was a great guy. Another book that is a good introductory book is Fine Ceramics by Norton. Norton was also at MIT, and I recommend that book. It talks more about whiteware ceramics, and that's the reason for the title Fine Ceramics. Well, another couple of books as you go along are about ceramic microstructures. So microstructure means that you're using an optical or scanning electron microscope to look at the micron level of mineralogy in a ceramic specimen. Now, we know that over time, the last 20 years, that nanoscience has become a very hot topic in ceramics. And a nanometer is 1/1000th of a micrometer, okay? Nanometers are down at molecular and atomic scale, whereas micrometers or microstructures are at the mineral assemblage scale of viewing a ceramic. Now, you may or may not want to become a microscopist. The pictures might become too complex, and it takes a long time to work at that. You might have a man or woman in your organization that's called a petrographer or microscopist, and that's what they do, is look at mineral assemblages in fired ceramics or even unfired ceramics. But the one by Fulrath and Pask, Ceramic Microstructures, has the best section on vitrification in a chapter that I've ever seen. So as you go along, you might want to look up Lee and Rainforth in ceramic microstructures. I lost my copy and had to buy one from a used bookshop on the internet, but I found it and I'm still using it. The book Ceramic Microstructures, Property Control by Processing by Leon Rainforth is also a wonderful book, and it's more involved with alumina silica compositions, alumina porcelains, zirconia is illustrated in this book. So it is really well written in terms of how to achieve properties that you want by processing and by firing. Another couple of books that we will get to thinking about the topics described in these books later in the course are given here. Introduction to Phase Equilibrium in Ceramics. If you can find that in your corporate library, we're not going to start with that immediately, but we will get to it in about the third or fourth lecture. So it's a very good description of two-component phase equilibrium diagrams. Just to make a comment about phase diagrams, when I was taught the subject of phase diagrams, how to use a map called a phase diagram, I was taught by starting from a melt and cooling off. Interestingly enough, I never made a ceramic from a melt and cooling off, although some people do, fusion cast ceramics. I made everything starting out at room temperature from particles. So the way that I use phase diagram is heating up. What happens when you heat a ceramic? So that's a good one to look up and have available. Finally, when we get to Unit 2 in the course, you might find it advantageous to find the North American Combustion Handbooks. The Volume 1 is the older book. The older book is going to be very useful to you in figuring out fuel combustion and ratio control of combustion systems. It doesn't deal with solid fuels at all, but we will go through a lecture on solid fuels just to make sure that somebody in some parts of the world using solid fuels has some background information. Volume 2 is an updated version of this. Now, North American has been bought by a larger company, so it's not called North American anymore, but you can buy the North American Combustion Handbook on the internet. And I'd like to say throughout my working career and visiting many ceramic engineers and many offices across the world, the North American Combustion Handbook is the one that I've seen in most offices in most locations. Engineers have this. So we will refer to that, and it would be good for you to be aware of this resource. You don't have to buy any of these books. You can take the course without any of them being available, but they're very useful for you to obtain, perhaps through interlibrary loan, or perhaps through borrowing from a colleague. Now, also in Unit 2 of this course, we're going to use a couple of downloads for the course. One of them is available through Morgan Thermal Ceramics. It's a thermal conductivity calculator. You have to go to their website and register in order to obtain that permission to go forward with the download. They want to know who's using it. We'll use it to look at furnace heat loss calculations. I've had personal difficulty registering on this website and downloading, but I already have the utility on my computer. So I hope you have good luck. You might want to go ahead and start at some part in Unit 1 of the course to try to download that and make sure that you have it available. The second download is called E-Solutions for Combustion. It is available as a download from the Honeywell company. The web address for this download is here. I've downloaded with ease the current version of this combustion utility. It's basically a combustion and furnace modeling app. It means that we don't have to do some of the things that people in ceramic engineering courses had to do for years manually, which was tedious and boring. Take my word for it. So we don't have to do combustion calculations manually. We can do them using this computer app. We also can model the furnaces, and we will model a batch furnace or an intermittent furnace in this course. A tunnel kill is nothing more than a sequence of different batch furnaces, if you will. So we will use that later on. So I use these apps on my office computer. I do not use them on my phone. I don't know if they work on the phone. Okay, well, a few final words for you. The key question in this course was how much temperature in class 1 of unit 1, how much temperature is required. We talked about kills a little bit and some of the historical development of kills, about heat rising and about different kinds of kills. But the key question was about how much temperature, and that comes from the type of ceramic that we are making, whether it's a vitrified ceramic, whether it's made by reactive sintering or flux bonding, if you want to call it that, or whether it's made by solid state sintering. So we'll have different thermal requirements based on the chemistries of the raw materials that we are using. So we're going to do quite a bit of this in unit 1. Then we're going to go into kill control, combustion kill control, furnishing the temperature that's required in unit 2, and in unit 3, which is the shorter of the units, some of the emissions from firing. I understand that many of you may be using electrical energy for heating. We're going to mainly talk about gas firing in unit 2, but the furnace heat loss utility will be exactly useful for you if you are using electricity for firing, or perhaps if you're using a solid fuel for firing. In unit 2, we'll work some problems. Those of you that took the drying course worked a few problems with psychrometric charts. We're going to work some problems in unit 2 that deal with combustion and furnace heat losses. Now, I will make a comment on using Zoom. You can pause as needed. You can see that spell checkers sometimes don't check correctly, but you can pause the presentation as needed. You can say, well, what did that professor say at that particular time? You can speed me up or slow me down using a speed control on the Zoom presentation. But the pause is very useful if you want to do a screen capture, and then you can print something. This is what I'm going to advise you to do when we get to phase diagrams that we need to use. Also, you can request PDFs of these lectures from the American Ceramic Society, and they will send them to you. So that's another way to review. I suggest that you sit in the course and take the course one time, and then I suggest you review it another time. So I'm expecting more classes in the firing course than I did in the drying course. The drying course was a course of 14 lectures, generally lasting an hour or a bit more. In this course, despite the time that I've taken today, I'm going to typically want to have the course to be 45-minute sessions. And we probably will have on the order of 25 to 30 classes. Just however long it takes to get through the course, with 45-minute classes. So that's our situation. You can do screen captures. You can access the lectures again if you need to review. You can obtain the PDF files of the lectures. So I'm looking forward to doing this. I'm going to try to teach you every single thing I learned in my career about the viewpoint of the thermal requirements of the ceramic inside the ceramic, the kill requirements outside the ceramic, and the smaller unit about environmental emissions. Now, class number 2 next time is going to be about physical and chemical properties that relate to firing. I'm not trying to make a lab person out of you, but topics like porosity and pore size distribution, you need to be well versed in understanding where I'm coming from and expressing compositions, for example. You're always going to hear me express the compositions as if the constituents were oxides. This is not always the case, but that's just the way we like to express our compositions. If you know a bit about Portland cement chemistry, you know that's what cement chemists do, is express all the compositions as if the metals were present as oxides. If you're a chemist by training, you're probably more accustomed to expressing the compositions as metals and nonmetals, but we will express the components of ceramic materials as metal oxides because that makes it easier for us to think about phase equilibrium diagrams, which are depicted in terms of metal oxides in ceramics. So next time we'll have a class on properties of ceramics and lab tests that reveal those properties to us to characterize what we've accomplished during the process of firing. So I look forward to working with you on this course. Just like the first course, you have the ability, just like the drawing course, you have the ability to meet with me and have Zoom office hours. That means an individual discussion between you and I using Zoom so you can ask questions and you can talk about your own particular problems. Just remember that you cannot give me any proprietary information. You need to use your organization's policies about handling proprietary information. And furthermore, I'm going to give you the best advice that I can in processing ceramics, but there certainly are opportunities to make products that don't meet specifications, and there are opportunities to have problems in firing, like accidents. And so I'm really not responsible for production quality or production safety in this course, but I will talk about these subjects quite a bit. So you have the opportunity to meet with me using Zoom office hours, prearranged. The way we have an office hour is for you to send me an email, and I'll be sure that you have that address, and we will arrange an office hour at a convenient time, realizing that I'm on New York time in the United States, and we'll find a convenient time for you to do this. I suggest that you set a goal of 1 or 2 classes per week. Particularly 2 would be a good number per week, and this particular course, since there are more lessons involved than there were in drawing. So if you meet that goal and you do your review at the end of this course, you're going to have all those abilities that I mentioned in the learning objectives. So I wish you well, and we will meet for the second class.